Welcome to Addressing the Hidden Costs of AI, presented by the SNIA Networking Storage Forum. My name is Eric Smith, and I'll be your host and moderator for today's webinar. And I'm pleased to introduce you to our expert speakers, Rob Davis, VP of Storage Networking at NVIDIA, David McIntyre from Samsung and a member of the SNIA Board of Directors. Unfortunately, David had a last-minute conflict come up, so I will be presenting his slides later. We also have Mishali Naik, a principal engineer and architect at Intel, and Justin Putzunik, an engineering technologist at Dell. First, a little bit about SNIA. SNIA is an industry organization that develops global standards and delivers education on all technologies related to data. SNIA is comprised of 200 industry-leading organizations, 2,500 active contributing members, and 50,000 participating IT end users and technologists worldwide. The SNIA Networking Storage Forum, or NSF, is an active group within SNIA that provides vendor-neutral education and insights for applying network storage standards and associated technologies to a broad spectrum of end-to-end solutions. Here's a list of just some of the technologies we cover. Now, some logistics for today. You can ask questions during the presentation by selecting the Ask Question option and entering your question. And we will either answer that question verbally during the presentation or afterward in a Q&A blog post. Also, in case you're curious, the slides are available at the attachment tab at the bottom of your console. Before we get started, let's take a quick look at the SNIA legal notice. This provides SNIA's copyright notice regarding the use of the material. SNIA is not providing any legal advice, and there are no warranties expressed or implied. So if you want to reference the material, please do so at your own risk. Here's the agenda for today's session. I'll start things off with a brief overview of the need for prompt engineering, or modifying how you put in requests into an AI chat. Mishali will then discuss the rapid evolution of AI. Justin will get into AI's impact on infrastructure. I'll then present David's slides about sustainability. And Rob will provide an overview of the fabric requirements for AI. And then finally, we'll have a little bit of time for Q&A. So as moderator, I get the honor of introducing the topic we're about to discuss. And in this case, I figured a good way to organize my comments would be to use a helpful graphic. And since this is a session related to AI, I figured why not use AI to create that graphic? So the images you see here are just some of the attempts to create it. Now, the journey to create these images started at openai.com and ended up being kind of funny, so I wanted to share it with you. I began by asking ChatGPT-4 to create an image. And ChatGPT helpfully responded with, sure, I can create an image for you. Could you please provide a detailed description of what you'd like the image to depict? And I was like, sure. I'd like an image that can be embedded into a PowerPoint presentation. I then provided a little bit about the formatting I wanted it to use, and finally the agenda topics. And a few seconds after clicking send message, it came back with an image that at first glance seemed pretty impressive. The accompanying text described what had been provided and ended with, this design should suit a professional presentation context well. Now, if you haven't picked up on the problem yet, the text embedded in the image is mostly gibberish. Now, at first, I thought the problem was due to mashing different languages together, so I asked it to make sure it was only using English. And ChatGPT helpfully told me the image created does not contain any text. It's purely visual. And thus ensued my first argument with an AI. It turns out getting ChatGPT to not include text required me to update my prompt or do a little bit of prompt engineering to exclude the words PowerPoint presentation. And this is the resulting image, which to be fair is still mostly gibberish, but now it's at least graphical in nature instead of written. The key takeaways from this experience for me were I really need to carefully review AI generated content. I also learned that prompt engineering is actually a thing. And finally, I discovered the most important lesson of all. When you ask an AI for help with a presentation, it's a bit like asking a cat to fetch. You're both going to be confused, but only one of you is going to end up with a PowerPoint presentation full of gibberish. And yeah, ChatGPT actually wrote that cat joke. So our first hidden cost of AI, arguing with AI, is out of the way. And now I'll turn it over to Mishali to talk about AI's rapid evolution.
Thanks, Eric. So as we all know here, AI is evolving rapidly. 58% of the CEO of public companies are investing in some form of AI. Gartner predicts that in this year, we will have 60% of the data that's used for AI projects would be synthetic. As we all know here, the speed with which generative AI has disrupted data science is unprecedented to date. With the large growing base of users that will be using generative AI, as Eric showed in the previous slides, AI inference will be driving the cost of compute, not pre training, as we would expect, and which has led to a wide spread of models, from large foundational models to a large number of small domain specific models. However, as we implement and use AI to solve problems, we have to use in a responsible and ethical manner. We must process data, train models, and deploy inference with these models in a responsible and ethical manner. Who we trust with our data during data processing, training, and inference is a key consideration. As we overcome privacy and security concerns, we can then unleash AI to its full potential while staying compliant. So we've seen the large foundational models, which are like the ChatGPT, Llama, and others, which are all in one, out of box, versatile models, and which serve as a foundational models for natural language conversation, programming, etc. And then hence called foundational models. However, these models are very large and very expensive to train. For example, like anywhere from $4 million to the order of tens of millions of dollars to train, and a reasonable sized model to infer from would be something around 3 million per month for inference. However, these models do have hallucinations and also the risk of exposing intellectual property. And given that they are trained on large data sets, they are frozen in time from sampling. Given these high costs for large foundational models, we've seen the emergence of specialized models, or what we call as domain-specific models. These models are 10 to 100x smaller than the foundational models and are specialized for the tasks. So enterprise can employ these set of small models for varying needs within an enterprise. These are more economical and can leverage the general purpose compute CPUs or general compute CPUs accelerated with GPUs and don't need specialized large scale GPU or AI accelerator based infrastructure. These can be continuously updated using approaches such as RAG, which is retrieval augmented generation. And they're more explainable and have source attribution. However, as we know, these are specialized models. They are focused and targeted towards a reduced range of tasks, and they do require fine-tuning and indexing for the task that is in mind. So as we look at the wide range of use cases where we are employing AI from the client to the edge to the data center, from classical usages of AI for image classification or object detection in the client side to document summarization across enterprises. At the client side, we're seeing small generative AI being employed for content creation, where videos are augmented with different images and forms, right? A person can be placed, in Venice with the use of generative AI models. Generative AI has also been employed for design. And as we look at the infrastructure, on the server side, we have CPUs with inbuilt AI accelerators or CPU and GPU, which are used for inference, which is the key that is driving cost, as I mentioned earlier, not training. Inference is driving the cost as we are deploying these generative AI and deep learning models. And so to support these varying use cases that enterprise are faced with, enterprise can employ these small specialized models, which are targeted for specific tasks on existing CPU-based infrastructure or by employing GPUs for accelerated results. And based on the needs of the enterprises, the infrastructure can either be scaled up with multiple CPU or AI hardware accelerators, or with a scale out where you have multiple of these nodes with AI nodes racked up or in a pod setting at a cluster and data center scale. As I summarize these use cases, as well, inference has less compute demands with the inference of small models, which can be performed on general purpose CPUs, to training, which you needs specialized GPUs and AI hardware accelerators, and mainstream inference and fine tuning, which is in between, which could be performed on CPUs or as well as CPUs. Accelerated with GPUs or specialized AI hardware accelerators. I'll now turn it over to Justin to talk about AI infrastructure.
Hello, everybody. This is Justin Tuznik. I'm in the Dell CTO office, focusing on AI and HPC. And I'm here to talk to you about AI infrastructure. How do you set it up? How is it different? Is it just another workload? And the answer, of course, is no. And it's not even just a question of grabbing a GPU and throwing it in an existing server and hoping for the best. One, we have a lot more than just GPUs accelerating our compute workloads and making AI work. GPUs are certainly a huge part of that, but FPGAs, other forms of coprocessors, DPUs are all things you need to be considering when building AI infrastructure. Networks, too, are going to be taxed and challenged by an AI workload. Uh, Many times the AI workloads call for both low latency and high bandwidth. Often there's 4 different network traffic types happening at the same time to feed an AI workload. So you'll have storage, you'll have control plane, you'll have back-end dedicated GPU networks, and then a general high-speed network on the front end. Storage also is going to see interesting challenges here, and while storage is probably not the number one thing getting taxed, it is certainly getting worked in different ways depending on the workload type. Training and fine tuning require high bandwidth, and that's mostly to keep the GPU utilization high. GPUs are hard to find, they're expensive. We want to make sure we're getting the most we can out of those assets, so we need to make sure that storage and network are not bottlenecking it. Conversely, inference requires less from a bandwidth perspective, but needs very low latency and high I/O capability. And that's because you're trying to, in many cases, interface with another human who's expecting a near real-time or real-time response. So the ability to handle that quickly is paramount. Next, there are also different software requirements here. This is very much a Kubernetes or a container-based workload, and so having the correct tools to manage that are very important. The end users especially will be using all new software. They're not going to be using traditional options here. They're going to be getting into different tools than they were, and so we're going to need to support those as well. And finally, we have different personas within AI workloads. Inference, fine tuning, and training are probably the 3 easiest ways to break them up, but that doesn't include everything. RAG, as an example, stretches across multiple of those, but they all need different things. And so therefore, when we talk about AI infrastructure, you need it to support multiple workloads or build multiple stacks for that. Additionally, AI infrastructure is generally much more taxing on the underlying hardware than what we saw with your kind of generic hypervisor that we've all been running for years with 60-70% memory utilization and fairly low CPU utilization. With an AI workload, your GPUs, as we said, we want to be maintaining as close to 100% usage as possible. And even the CPUs and memory will be getting taxed more. Memory in the 70 to 80% range, CPU in the probably 60-ish% range. So we're seeing the hardware get pushed a lot harder than we do in other workload types, sort of across the board. Finally, something to note on all this is AI infrastructure from an optimal configuration standpoint is very much a moving target. And it's a moving target because of multiple things that are happening. We have one set of users and one set of model creators trying to make things more efficient. They want to be able to either do more with what you have or do the same thing with less, right? How do I turn a model that is 13 billion parameters into a 7 billion parameter model, but not decrease the quality? At the same time, we have a different group of individuals and companies out there trying to make bigger and better models. They want higher quality outputs. They want less hallucinations. And this is where we're seeing parameter counts upwards of 1 trillion parameters. And we'll see that out in the open. You'll be able to download that within this year, I would expect. Finally, we're seeing a divergence from the LLM dominated stacks of today to where we'll have more video and image and that sort of thing coming in, which will change our usage parameters, especially in relation to storage. So just note that while this is everything as of today, like I said, this is all changing very rapidly. And some of these trends we've talked about, but just kind of looking forward, things to note. First, we're seeing huge adoption across the board, fine tuning, inference, large companies, small companies. Everybody is getting into this, and it's not just a question of noise and individual data scientists are playing around. Many companies have hundreds of pilot projects, while at the same time we're seeing most companies having at least some use cases now in production and getting good ROI. So that's something to keep in mind, that it's not just a question of talking anymore. Folks are out there doing. Silicon diversity is only increasing, and what we mean by that is the companies offering solutions in the AI infrastructure space, whether it be chips or larger architectures or what have you, is continuing to accelerate. We've seen no slowdown in new companies and new options out there, and expect the next couple of years to see um, a huge boom in this area. Um, Most of these, like I said, we'll touch on, but the last one here that I want to make sure gets mentioned is open and transparent. Across the board, as an industry, as a customer base, everyone has adopted open source. And this seems to be an area where it's almost just default that that's what you're going to do. Permissive licensing models, transparent data usage, industry standardization, all this stuff is kind of part and parcel of AI at this point. So one thing I certainly want the practitioners of SNIA to be thinking about is power usage. Nothing's free in this world, and AI loves to gobble power and cooling. So, and what we're seeing is a hockey sticking trend here, where despite previous generations slowly creeping up, it's going to accelerate. We're seeing in the GPU chips upwards of 500 watts per socket becoming more and more commonplace in the very near future. And when you clear 500 watts, really air becomes a problem as far as its ability to cool that much. So you're going to need some form of liquid, whether it's assisted, whether it's exchange, whether it's DLC. If you're not thinking about how do I add liquid cooling to my data center, now is the time to start. Now, the nice part is the density we're able to achieve is excellent. So I know a lot of folks have always been challenged by sort of a per rack kW limit. This is a great time to rethink that. Do you worry about the per rack, or do you worry about per room or per data center floor space? So it's something to start thinking about, is can we change sort of the metrics that we use, especially as we start to move into liquid stuff, like hotspotting becomes less of a problem. So be thinking about this. This isn't going to be a short-term trend, and we're going to see a lot of it. So be worried about power and cooling. Another thing that I think is going to be great for the industry as a whole is silicon diversity, but with standardization. And in fact, the diversity is pushing the standardization, as backwards as that might sound. And the reason for that is everybody wants to make a cool chip, but nobody wants to design a motherboard or what a daughter card looks like, or any of that sort of thing. So OCP, their DCMHS standard, is something that a lot of companies are really starting to take on. And certainly when you're considering infrastructure options, I would be asking about DCMHS compatibility. Um, Essentially, if you think about it, why do we have different power supplies from a dozen different vendors and a dozen different OEMs when they're all about the same efficiency level, they're all about the same output, that sort of thing? We all saw in the COVID days and the supply chain crises, uh, what if everyone just made the same power supplies? Wouldn't that just be easier for everybody? Same with I/O connectivity and some of the OCP 3.0 NICs, of course, have seen great adoption already, and we expect to see more and more of that in the coming year to 2 to 3. So, like I said, be asking about DCMHS when you're thinking about this sort of thing. Finally, let's talk a little bit about training and fine tuning, and how to mitigate demand and need for huge infrastructure just to do AI. Lots of folks want to do training until they kind of start to dig in a little bit, and luckily the industry has kind of already provided us with the answer, and that is pre-trained models that you do fine tuning on. To give you an example here, if you wanted to train a 70 billion parameter model, which is a medium-sized model that'll give you high quality, and you wanted to do that from scratch, you're going to need 128 GPUs. That'd be 16 8-way servers, running at 100% utilization for 24 days straight, with no bottlenecks, no network issues, no storage in the way, nothing. And you're looking at 105 megawatt hours of power usage over that 24 days. That's a sustained rate of 174 kilowatt hours over that whole run. Now, if we take a existing model and we do what's called a fine tuning job, which is where you take an existing model, add your company data to it, and run essentially a couple more iterations of the tuning, you could achieve a similar quality result of the same size model, still 70 billion, but with a single server with 8 GPUs. Now only needs 5 days to do that. So you're talking barely 1,300 kilowatt hours of power usage over 5 days. So you can see this is a huge step down, both in the number of servers you need, the amount of power, the time to value is far better when we look at fine tuning. Now emerging as we speak are also additional options beyond fine tuning. Things like RAG are making this even easier. So stay tuned for more about that. But again, fine tuning, to reiterate, it really lets you focus on what your company does. If you're trying to start from scratch, you have to collect all that base data to train the model how to even sound like a human, how to even understand all the context. With a fine-tuned or pre-existing model, that's already been done for you. All you've got to do is get your company data, which is in and of itself an enormous task in many cases, and work on that and connect that to these servers, and away you go. So you need less infrastructure, you need less storage, your time to value is better, and finally, all of this AI stuff is hard to find the people to actually do it. If you don't have in-house skill sets already, trying to find folks to stand it all up for you and run it is hard and costly and takes a lot of time. So anything we can do to cut down on the load on those folks or cut down on the total number you need, that is a good thing. Final slide here, just to talk a little more about RAG, because I know it's super hot and it's going to be a big topic really for this whole year, I think. It's really the next evolution beyond fine tuning, which certainly is not going to go away, but this is another way to augment it. And this is an idea where you take your company data, you can put it into a vector database, and that works with your pre-trained LLM to very rapidly hand out answers to folks, whether it's a chatbot, internal or external. And with that, I'll hand it over to what would have been David McIntyre, but unfortunately he had a last-minute conflict, so I believe Eric is going to be taking us through this part.
Thanks, Justin. All right, so covering for David here, as the deployment of AI ML solutions continues to accelerate, and with large language models now exceeding 1 trillion parameters, we need to make every effort to optimize the infrastructure, and this includes optimizing individual components down to the chip level. Now, to quantify the benefit that we receive from these optimizations, we need to consider not only the cost per unit of performance, but also the amount of power consumed, and find a balance between them. One optimization that can reduce power consumption and related costs is to follow a data-centric computing approach and make use of application-specific accelerator solutions, such as GPUs, DPUs, and XPUs. For maximum benefit, these accelerators can be physically located in the same system where the data resides. This can reduce the amount of data that needs to travel across the network and improve overall system performance. Also, by using accelerators, we free up the host processor complex from performing data management tasks like compression and traffic management, allowing more of the CPU to be used for end user applications. Data center infrastructure is composed of many individual components. Therefore, power optimization across componentry can provide a cumulative effect on overall power savings. For example, solid-state drives or SSDs are being designed to optimize cost versus performance and performance versus power consumed. By working hand in hand with application developers, a designer's recipe of NAND media types such as SLC, TLC, QLC, along with DRAM cache design, improves read-write performance. Adding advanced controller functions to these SSDs allows for intelligent power modes by predicting and adapting their operating mode to account for hot and cold data access patterns. Furthermore, the low power or LPDDR roadmap contributes to improved power efficiency. Increasing the density of NAND media also improves the efficiency by supporting capacity requirements with less silicon. Innovations in low power DRAM design and production are also helping. For example, extreme ultraviolet or EUV lithography is an advanced semiconductor fabrication process technology that improves power efficiency across the DRAM die. When combined with the design techniques, including dynamic voltage frequency scaling to align with workload requirements at the component level, both performance and power consumption can be improved for a better performance per watt metric. Additional processing techniques include high-K metal gate and through-silicon via technologies, along with advanced packaging such as high bandwidth memory. The memory capacity roadmap continues to be enabled by advanced packaging and process technologies while providing a component level contribution to power savings. So in summary, component level design innovations can contribute to data center infrastructure cost and power improvements, and they will make up a big part of the innovation required to deliver AI ML solutions in the future. And with that, turn it over to Rob for Fabric.
Thank you, Eric. Hello, everybody. First, I want to thank Snia for letting me present today. One of the great things about being in the computer industry is that it never gets boring. It's always changing, and the most exciting changes usually involve higher performance, like GPUs, for example. Everyone wants a faster computer, which is a good thing, but the trouble is the new higher performance is not always usable, at least right away. That is because often there are bottlenecks in other parts of your application's data path not designed to handle the new performance. Then, once that bottleneck is resolved, like the game of whack-a-mole, it only reveals the next one. So we get excited about this new performance, but it often takes a while to really get it. A perfect example is hard drives. The storage industry, with the advent of SSDs, they had amazing performance compared to the hard drives they were replacing, but at least in the beginning, it was only on IOmeter. Before we dig into that, though, please notice the plus sign on this slide. It is there because hard drives have not gone away, and in fact, hard drive makers are still innovating. But of course, now they are focused on a different use case than the mainstream storage they did in the past. So going back to SSDs, what was that amazing performance compared to hard drives? They were 1,000 times, an order of magnitude faster. When they first came out, SSD performance was amazing on test software, and they made your laptop boot faster. But most applications, although somewhat faster, were not 1,000 times faster. They had hit the whack-a-mole bottleneck. To get there, first we needed a new hardware interface and block storage protocol designed for SSDs, not hard drives, called NVMe. Then new network protocols for moving the faster SSD storage across the network and taking advantage of their lower latency. This is where NVMe over fabrics and RDMA came in. And of course, we needed faster wires to make use of the faster protocols. Another whack-a-mole. You get the idea. So where do GPUs fit into this? Well, guess what? It's happening again. A new game of whack-a-mole, but this time with compute. GPUs have amazing performance compared to CPUs. Notice the plus sign again, though. CPUs are not going away, and in fact, CPU makers, my company being one now, are still innovating like crazy. For example, ARM CPU technology, like what's in your phone, is now being souped up like a stock car for racing and is now available in high-end servers. So back to that amazing performance that GPUs have compared to CPUs. By coincidence, like SSDs and versus hard drives, they are 1,000 times faster. But this is because, as we know, CPUs have tens of general purpose cores, but GPUs have tens of thousands of special purpose cores. But as I'm sure you've probably guessed, these tens of thousands of special purpose cores are creating a lot of compute performance, but along with it, some whack-a-mole bottlenecks. Starting with the network. Intuitively, one assumes we need faster wires to make use of the faster compute. And it is true, because AI problems usually don't fit in one GPU. For example, according to a Google search, training ChatGPT on a single GPU would have taken 355 years. But by clustering 25,000 GPUs with a network, it was done in days. The higher network speeds are also needed to get the data to the GPU applications. Like teenagers, GPUs are always hungry, but instead of being hungry for whatever is in your refrigerator, they are hungry for data. As the first chart on the left shows, dataset sizes for CPU applications are typically gigabytes in size, but for GPU applications, the dataset sizes are measured in terabytes. So getting data to them is like the difference of feeding a large family versus feeding a small city. And this difference is only getting bigger by the day. The second chart here shows the change over 4 years in the number of parameters used in very popular AI large language models. Look at the difference in just 4 years. It starts with these models using 100 million parameters 5 years ago, which already seems like a lot, and goes to almost 1 trillion by 2022. With SSDs, remember, we needed not only to upgrade to faster network speeds, but also invent new ways of interfacing to them, like NVMe, to be able to fully utilize the high performance storage they provided. With GPUs, it's the same. Faster networks to feed them the data they need is not enough. This is not only because of the enormous size of the data sets, but also because of how fast GPUs can process the data they are given. If you use traditional storage stacks, like we did with SSDs before NVMe, they work fine, but your expensive GPUs can be idling, waiting for data. Not only idling, but using power and cooling while they're waiting for data. If you compare the amount of time it takes for a CPU to process and perform its storage I/O cycle to that of a GPU, as I do in this diagram, you can see the issue. If the I/O speed is the same, the GPU will be waiting for data to be loaded or the results of its calculations to be stored. In order to efficiently use the GPU, you must improve the storage I/O performance. To solve this, we needed to invent GPU optimized storage stacks. They bypass the hosting GPU's storage stack and move the data directly from the local SSD memory to the GPU memory with DMA. For remote storage, they use RDMA, but the process is the same. To remove the CPU from the data path, both latency and bandwidth to the GPU are dramatically improved. There are many network choices for AI applications depending on the performance you need. From the highest performance GPU to GPU chip fabrics like an NVLink to traditional Ethernet with IB somewhere in the middle, InfiniBand somewhere in the middle. As you can guess, the cost curve follows the performance like it always does, but you can actually optimize traditional Ethernet to get it very close to InfiniBand performance while keeping the Ethernet cost structure. To do that, some whack-a-mole bottlenecks need to be knocked down, of course, without, of course, modifying the Ethernet standard. So first thing you need to think about is the elephant versus the mouse traffic problem. AI workloads have many more large elephant messages than traditional applications. So you need to keep the small mice messages from getting stepped on. Second, you need to not only reduce the latency as much as possible, but also make it consistent, meaning no long tail latency, which creates jitter. Message delivery jitter means GPUs are idling, burning power and cooling again, and not doing work, but just waiting for it. And finally, you need to make sure the bandwidth is consistent to all the nodes, or like the jitter, the slow data transfer means the GPUs are idling. The ones that have already gotten their data are idling, waiting for the one that's waiting on it. Here's an example of what AI optimized Ethernet can do. This is real test data from SpectrumX AI analyzed Ethernet running on AI applications, real AI applications. The graphs on the left show the bandwidth improvement when comparing Rocky traffic on traditional Ethernet to the same AI application traffic on AI optimized Ethernet. Rocky traffic, by the way, is RDMA. The graphs on the right show the latency jitter improvement when comparing Rocky traffic on traditional Ethernet to the same AI application traffic on AI optimized Ethernet. Understand that this is an apples to apples comparison between today's highly tuned Rocky traffic on a traditional Ethernet to the same AI application traffic on AI optimized Ethernet on the same switch. One more optimization for AI on standard Ethernet is to simply wire it differently. It seems too easy, but it really works. Instead of designing your wiring plant to optimize for cable lengths, design it to optimize GPU server connectivity. For AI cluster traffic, this gives you 2 less switch hops, lowering your latency automatically, and reduces your spine traffic, which is the highest potential congestion point. The final thing on the network to think about when designing one for AI is this. Instead of measuring the cost of the network by the price of the components, measure it by the cost of cost per bit transferred. The graph from this study I'm showing here is a little dated, but the concept is not. Because the most important thing is to keep your expensive GPUs fully utilized. And as I hopefully have shown you, the network is a very important part of that effort. Back to you, Eric.
Thanks, Rob. So just want to summarize, what we said. Using generative AI requires patience and attention to detail. if you don't get what you're expecting, maybe do a little bit of prompt engineering, and it might change your result. AI is rapidly evolving, and there are many use cases, not all of which require access to GPUs. The infrastructure required to train or fine-tune a model is highly specialized, resource-intensive, and is continuously being improved. Optimizing the components used to create infrastructure will reduce power consumption and your time to train. And as Rob was just telling us, the network needed to interconnect your AI infrastructure far exceeds anything that enterprise environments have seen to date. It's quite a change. So with that, we have a little bit of time for Q&A. The first one that I wanted to take was, will this video be available after the talk? Yes, you can find it on the Bright Talk platform afterwards. You could Google Bright Talk SNIA and it'll bring you right there. So that's that. Another interesting one, I'll tee one up and then we'll go another one after that. Fundamentally, is AI radically changing what is required from storage? Or is it simply accelerating some of the existing trends of reducing power, higher density SSDs, and pushing faster on the trends in computational storage, so on and so forth? Yes, it's a fundamental change. It's really pushing the requirements for storage. It's primarily file and object. So don't think blocks. I think files are objects, and scale out seems to be sort of the way that you're going to be able to handle the massive amounts of data that needs to be ingested to just get your training started. And then there's checkpoints that you're going to have to worry about periodically. So it's a big change, and it's really forcing people to think differently about their storage. So there's probably a lot more I could say about that. Does anybody else have anything that they'd like to add?
One thing I'll add, Eric, is not only is it pushing storage harder than it's pushed, in many cases, is the idea of data management and data prep. We're having to do a lot more of that now that everything is file and object, and that's critical to successful AI deployments. So recognizing that you need a strong discipline around how, where is your data, how do you get it closer to your GPUs, but then what is its form, and doing a lot of that tuning on the data and getting it into a consistent format can be critical to project success.
And understanding that you have all different kinds of data now. You have video data, you have text data, you have, just so many different kinds that are all involved in the training process.
Yep. Great points. Let's see. There's another one in here related to networking specifically, so we'll just knock that one off. Fiber channel seems to have a lot of the characteristics required for the fabric. Could a fiber channel fabric over NVMe be utilized to handle the data ingestion for AI component on dedicated adapters for storage? I would never say never, but I would say that right now the speeds being required for like data ingestion, for example, they kind of start at 400 gig and go up from there. And so, fiber channels right now, it's sort of 128 gig is the max speed for them. So just from a feeds and speeds perspective, it might be a little challenging, but like a FC, I've heard about rumors about an FC RDMA project. If you were able to tackle the physical limitations, maybe that's an interesting area.
I think the other thing to think about, though, Eric, is what you said earlier. Object and file are the most important pieces of interfacing to GPU applications, whereas fiber channel is pretty much blocks.
Yep. Yeah, that's why I was going with FCRDMA. I didn't know if maybe that could help with that, but yeah, fair enough. Let's see. There's one in here about what is the difference between peak inference, mainstream inference, baseline inference, and endpoint inference, specifically from a cost perspective? Anybody want to try and tackle that one?
Yeah, so endpoint inference is what the inference that is happening on client devices, laptops, smartphones, right? So where you have much smaller models which are optimized for very constrained power envelope, right, for on these smaller form factors. And the peak inference, you can think about something like a ChatGPT or Bing's AI chatbot, right? Where you do need large infrastructure to serve the inference of the a ChatGPT, right? Where you will need specialized hardware infrastructure, GPUs, or AI hardware, specialized AI hardware accelerators. And then mainstream and baseline inference is somewhere in between, where you're tackling much smaller models, which are what we discussed earlier as specialized models, right? Like, for example, you have a Mistral 7 billion model, which you have fine tuned for your enterprise usage of, let's say, document summarization or to find insights in a sales pipeline. So those usages can employ much smaller models, and hence the requirements do vary in terms of so in terms of cost. I think the question was around cost. So the deployment of these models for inference would be low cost compared to like a peak inference like a chat gpt in terms of infrastructure. And so some of these baseline and mainstream inference models can be served, just with even with a cpu alone, or with a cpu plus a gpu, or with cpu plus a few gpus, or cpu plus a few ai accelerators. So, and many of the CPUs today do have inbuilt AI accelerators, so which do provide an optimized cost solution for this baseline and inference, which will be the a typical scenario in many of the enterprise usages.
Cool. Thanks, Mashali.
I'll pile in there a little bit too, if that's all right.
Yep.
So like Mashali said, right, when we think about edge, it's pretty much, yeah, what is your edge for you? Edge is a very um, ill-defined term at this point, because it does cover so many things. You can do edge inference on a smartphone, that can be on a computer, that can be on a core data center, can even be considered edge. But the other terms are more interesting, because when we first started doing a lot of this, we really thought about inference as sort of an exchange, right? You had X number of tokens coming in as the query, and Y number of tokens going out as the response. And we tried to measure really the end-to-end time there as sort of the be all end all um, metric, and then cost based off of that. What we found very quickly is there's enough variance that a better way to do it is to really have a two-pronged approach: time to first token back out, and then subsequent tokens thereafter, how long it takes. And that allows for a much more fine-grained answer while still being kind of usable at a high level. And this is why too is, like, you'll see large providers like ChatGPT, they charge per token now in many cases, is because that's the easiest way to do it. And then that also allows you to better understand, humans read at a given speed, right? If you can produce a token per 100 milliseconds, let's say, the average human can read at about that pace. So as long as you can meet certain requirements for how quickly the answer is coming back, then you're good. So all those things need to be kind of considered when looking at cost, and aggregate inference, or peak, as you said, peak or aggregate, either word, is great from a hero number perspective, but going kind of one layer down and understanding that how many concurrencies can you handle, and then what's the rate that you can serve up tokens is really what helps, and is useful.
I think it also depends a tremendous amount on the edge application. As you said, edge is not exactly defined. I mean, if it's an anti-missile system, you probably want a whole different approach than if you're answering questions about product colors.
All right. Thank you. I think we have time for at least one more, although we have plenty that we're not going to get a chance to get to. And as I mentioned earlier, but keep them coming, because we will answer them in a Q&A blog post that will be hopefully up sometime next week. But All right. So one question: what is the presenter's view about the industry trend to run workload or train a model? Is it in the cloud, like with AWS, GCP, or on-prem? Who would like to start with that one? I'll start. It depends, right? There are plenty of, just getting started, just going out and playing with AI and generating, training a model, and if you don't have hardware, then you're best off going to a cloud and seeing what you can do. There's a bunch of simple things you can do with like Colab, and if you go out and check out Hugging Face, for example, there's a bunch of different tutorials you could walk through, and you get a feel for just how simple it can be to start getting involved in this space. But then if you're going to be training the next large language model, you're running that on your own premises, and I don't think you're going to try and do that in the cloud. It would be cost prohibitive. I don't know if anybody's done a cost comparison between that, but if it has been, Justin probably knows about it. But so that's what I would say. It depends, and there are very valid reasons for doing both.
Yeah, I can jump in here. Yeah, as Eric alluded to, we've done some studies around this. There was even a version of this deck, I think, that we tried to present some of them, and it's at the end of the day, there is such a it depends answer to it. That being said, from a trend perspective, I want to mention you really have, there are three choices to always keep in mind. You have the cloud providers, right? The plus and minus there, of course, the plus is speed, right? You can literally log on, enter a couple of commands, and you've got access to a huge amount of resources. The downside to that is your cost per GPU hour is relatively high compared to other options. At the other end of the extreme, of course, is something on-prem, whether that's under the desk of a data scientist or in a data center, and it's thousands of GPUs. I would say per GPU hour, that can be very inexpensive, but you have to have capital up front. You have to have the data centers for it. An interesting middle choice that is emerging is this idea of the tier 2 cloud service provider that is a specialized service provider just for really GPU and AI workloads. Most of them are fairly new, so the facilities are very efficient, and really all they're trying to do is compete with that on-prem GPU per hour cost and undercut the traditional large cloud providers. So there's definitely different choices depending on the size of the project and the speed that you want to move at.
Yeah, and also one other consideration is, as Justin and Eric mentioned, basically is the how much of your AI workflow will require, either a GPU or an AI hardware accelerator, right? So in the cloud, having reserved instances with these AI accelerators when you're not using them would be wasted cost, right? Whereas, maybe looking at on-demand instances, right? Whereas in on-prem, you could share the infrastructure within your company with other groups that may be using AI for their use cases. So it's more like the cost that's shared across the different groups within an organization. Whereas and in cloud you can look at on-demand instances versus reserved instances and the trade-offs.
I think another good advantage of these up and coming tier 2, if you want to call them, cloud providers that are focused only on AI is that they are ahead of the curve on learning all the tricks to make these AI applications, as most efficient as possible, because that's how they're making their money, by making them as most efficient as possible. So if you're going on-prem, you're going to a certain extent, learn a lot of these by trial and error where they're already there.
All right. So we got at least 10 questions that we were not able to get to. And again, we'll put those into a Q&A blog. But please, before you go, please do rate this webinar and provide us with your feedback. We use it to improve and we greatly appreciate it. The webinar and a copy of the slides are available at the SNIA Education Library. And then, like I said, we'll post that blog later on. And don't forget to follow us, SNIA NSF. Thank you very much for your time. We really appreciate it. Hope you found it valuable. Thank you.